is the second part of the first section of the forces topic. Introduction to all the different types of forces. And in part B, I'm going to give a definition, a simple definition, and an example with a diagram for each of the forces that were listed in part 1. Now, what I will be doing is pairing the forces up together in examples where it makes sense to put the forces together. So I won't necessarily be doing one force at a time. I may be doing 2 or 3 forces at a time in an example, in a real-world setting, where, again, it makes sense to put all those forces together in one example. The first 2 forces that I'll be pairing up to talk about and give an example of are the gravitational force and the normal force. The gravitational force is defined as the force that one object exerts on another due to their masses. Both objects have mass, therefore they exert a gravitational force on each other. The normal force is a perpendicular force that a surface exerts on an object. So the object is resting on the surface attempts to support the object. If the normal force is great enough, the object will not break through the surface. If the normal force is not strong enough, then the object will break through or sink into the surface. All right, so let's give a nice, simple example of a gravitational force and a normal force. All right, so we have, for example, right, a surface. It could be the ground, a floor, a tabletop, it doesn't matter. And we'll put a box on the surface. Now, the gravitational force, in this case, we're going to talk about the gravitational force of the Earth pulling the object down. So, Fg. We'll call it negative Fg because it's a negative force. The Earth is pulling the object down. Now, if the table is strong enough or the floor is strong enough, it's not going to allow that object to break down into the table or break through the floor. The floor or the table is going to provide a normal force, a supporting force that is directed upward on the object. And that normal force is going to be the same magnitude as the weight of the object, Fg. The gravitational force is the Earth pulling down on the object, that is the object's weight. The normal force, if the surface is strong enough, prevents the object from sinking down into the surface. Now, for the record, right, here's the surface. Note that the normal force is perpendicular to the surface. And the weight is always directed straight down toward the center of the Earth. Now, just very, very briefly, if the object is resting on an incline, all right, here's the surface, here's the object, all right, our box, then the weight of the object still goes straight down, but the normal force is perpendicular to the surface. So, here's the surface, the normal force has to be directed perpendicular to the surface. And it is also no longer the same magnitude as the weight. Right? It would be there. F normal. Okay? So that's an example of the gravitational force and an example of the normal force. We'll go into much more detail in later sections. The next two forces that we'll put together to give a nice simple example would be the applied force, and that would be any time a person, animal, machine, or some other object pushes or pulls on a second object. And the friction force is a force between surfaces that are contacting or touching each other. The friction force opposes relative motion between the surfaces, and it's caused by electrostatic interactions. All right, so let's look at this in just a little more detail with a nice, simple, real-world example of the applied force and the friction force in action. I'm going to take the same surface that we used in the previous example. We're going to take a tabletop or a floor or the earth, it doesn't matter, and we're going to put a box on top. Now, obviously the box still has its weight and it still has a normal force. The box is not sinking or breaking into the surface. I'm going to ignore those forces for now. So let me get rid of them, and we're going to focus on two new forces. We're going to focus on the applied force and the friction force. But keep in mind, the gravitational force and the normal force in this example are still there. So let's say that somebody is pushing this box. I'm over here trying to push this box, trying to get the box started. So this would be an applied force on the box. I'm pushing it horizontally. Now, the box is not moving yet. I'm having trouble getting the box to start moving. So the force that is opposing me would be static friction. So that would be negative FFS. Since the box is not yet moving, this is called static friction. Now, once I get the box to budge and it starts moving, and in this case I'm going to push that box at a constant velocity to the right, then that becomes kinetic friction. So my applied force is to the right. Both types of friction are to the left. They oppose the motion that I'm trying to get the box to follow. They're directed against me to the left. Let's look at another example. The next two forces that we'll look at together in a real-world example will be tension, which is the force in a string, rope, wire, or cable, you get the idea, that is being used to pull or hang an object. The word hang, the word suspend comes to mind. In a suspension bridge, the cables, the roadbed, the roadway is suspended by the cables. The cables are holding up the road in a suspension bridge. Centripetal force is any other force that is directed toward the center of the circle, and this causes an object to move in a circle. Let's look at a nice, simple example of tension acting as a centripetal force. If you take a rock or any other object and tie it to a piece of string, and you swing it around your head in a horizontal circle, a flat circle. Now, what I want to do is look at that flat circle from up above and draw it that way. All right, so here's the rock. Here's the string. I'm standing here. This is my hand. swinging the rock around in a circle. All right, remember, you're looking down as I'm swinging the rock around my head in a circle. Don't do this. If you let go of that rock, you're going to hit somebody, and that would be bad. Okay, so the tension is in the string, right? The tension, right, is pulling the rock in this direction. Right, so there's the tension. Now, the tension and the centripetal force are one and the same. The centripetal force is toward the center of the circle, FC. Right, so this is an example of tension acting as a centripetal force. And by doing this, it keeps the rock going around in a circle. So when the rock is over here, the tension and the centripetal force are that way, toward the center. When the rock is over here, the tension and the centripetal force are that way, toward the center, etc., 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 as the rock continues to move around in a circle. The next two forces that we'll use in a real-world example are the gravitational force again and the buoyant force. The buoyant force is the upward force exerted on an object that is immersed in a fluid. Right? It might cause the object to float. If the buoyant force isn't strong enough, the object will sink. So for our example of the buoyant force, let's put two different objects into water. Here's the surface of the water. And let's put a block of metal into the water. I think we know that that's going to sink. And it's sinking because the weight, the gravitational force that the Earth exerts downward, right, negative Fg, has a greater magnitude than the buoyant force that the water is able to supply to the object in the upward direction. So there's the weight down. Here's the buoyant force up. And since the weight down is greater than the buoyant force up, the object, right, is sinking down in this case. Now, what about an object that is floating? Right, let's put an object here. Right, this would be some kind of plastic, or even like a little boat, right? But in any case, this object is floating. This object is floating because the weight down, right, negative Fg in this case, is balanced by the buoyant force upward. I'm trying to make them the same magnitude. That looks about right. We'll make that a tiny little bit longer. Okay? So negative Fg, yeah, okay. Positive Fb. All right? So in this case, the object is floating because the net force here is 0. You could say that the object is at rest. All right, so again, an example of the gravitational force on the object directed down, and the buoyant force on the object, the fluid, in this case a liquid, water, supporting the object a little bit, not enough, so the object sinks, or supporting it sufficiently that the object is able to float. And now a nice simple example using an airplane of what we would call thrust. Thrust could be propelling an airplane forward, or propelling a car forward. Thrust is caused by either mechanical propulsion, as in the case of a car, or gases coming out the bottom of a rocket and, due to Newton's third law, pushing the rocket up, or gases coming out the jets of a jet airline and pushing the jet forward due to Newton's third law. And we will get into Newton's third law later. So that would be thrust. Lift is causing a plane or a helicopter to move up into the air. You don't want lift on a car because that would be dangerous. The car loses contact with the road and the car could flip over. This can happen with race cars. You have to design race cars very carefully so they don't lift. Drag is really air resistance, and there's drag on an airplane. The airplane is trying to go through the air molecules are rubbing up against the airplane, causing drag. It's a form of air resistance, which is a form of friction. Cars, race cars especially, and regular cars also have drag. You try to design an airplane, a helicopter, a race car, a regular car, to minimize the drag as much as possible because drag wastes fuel. All right. To illustrate the forces on a typical vehicle, an airplane, the forces of thrust, drag, lift, and our old friend weight, gravitational force, we're going to use the example of an airplane that's already up in the sky and flying forward at constant velocity. So, here's the nose of our plane. Here's one of the plane's wings, the plane's tail, and the plane's other wing. We'll give the plane jet engines. Here's one jet engine here on this wing and another jet engine here on this wing. Now again, our plane is flying to the right at a constant velocity. I'm going to get rid of that. All right, you can keep it there if you're taking notes, but I just don't want it to get in the way of the forces that we're going to be drawing. So again, we'll put a dot, all right, more or less in the center of the airplane. Now, the gases are coming out the back of the jet engine, and according to Newton's third law, this causes a thrust force, a forward force, in the opposite direction that the gases come out of the jet engines. So since it's going to the right, we'll make that a positive thrust, force TH for thrust. Now, the friction or air resistance in that direction is called drag. And because the plane is flying at constant velocity, I'm going to make the drag equal in magnitude to the thrust. All right, so I'll do my best. Oh, okay, it's close. Maybe this should be a tiny little bit longer. All right, so there's the drag. Okay, and we'll label that, since the drag is opposing the forward motion of the plane, we'll label that negative FD. Now, the lift force, all right, is the force that keeps the plane up, all right, and that's going to be, since it's up, it's going to be positive FL, the lift. And of course, the reason we need an upward force, a lift, is because the weight of the plane is directed down, negative FG, toward the center of the Earth. All right, and again, this plane is flying at constant velocity in this direction, and the plane, in this example, we'll say that it's not moving up or down. All right, so we have, again, the forward force, the thrust. We have the friction, the air resistance, which for an airplane we will call drag. right? Thrust, drag. We have the weight of the plane, which is directed downward. That's a downward force. The Earth is pulling the plane down. And the lift force is balancing the weight force and keeping the plane up. All right? The next group of forces that I'd like to put together for a real-world example will be our old friend, the gravitational force, which we've defined several times, the electrostatic force, which is an attractive or repulsive force between charged objects, and the strong nuclear force, which is the force that holds quarks, protons, and neutrons together. All right, let's take the example of two protons. Now, in a later section, we will use equations to actually calculate the gravitational force between two protons and to actually calculate the electrostatic force between two protons. But in this case, we're just going to talk about it mostly qualitatively. So if we have a proton, all right, I'm going to put the plus there, but I'm going to get rid of that plus in just a minute because I don't want it getting in the way of my force vectors. So here's a proton, and here's another proton, all right? Because they're both positive, they repel each other because of the electrostatic force. So we have Fe, right? And to the right, we'll make that positive Fe. And to the left, we have negative Fe. They repel each other. Now, the gravitational attraction between the two protons, because they have mass, is there, but it's smaller and weaker than the electrostatic force. So let's draw the gravitational force, all right, Fg, and this one, negative Fg, smaller than the electrostatic force. Now, in actuality, it is a much more dramatic difference between the electrostatic force and the gravitational force. I can't do the scale of the differences justice in this diagram. Suffice to say, the electrostatic force has a greater magnitude than the gravitational force. The electrostatic force that is pushing the protons apart has a much greater magnitude than the gravitational force that is trying to keep them together. So the result of putting two protons a distance apart is that they are probably going to head in opposite directions as fast as they can. Now, if you move them very, 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 very close together, on the order of the distance of the diameter of a nucleus, then what happens is the strong nuclear force is able to take over. The strong nuclear force is much, much greater at very, very, very small distances. So, as you move those protons closer together, right, you still have the electrostatic force that's trying to push them apart. You still have the gravitational force that's trying to bring them together. But the reason that the electrostatic force doesn't win in the case when the protons are pushed together in the nucleus of an atom is that the strong nuclear force takes over. Right? Force, strong nuclear, that's in that direction. And force, strong nuclear, in that direction. At very, very tiny distances, like in the nucleus of an atom, two protons, that would be helium. You need two neutrons too. The strong nuclear force takes over, and it overcomes the electrostatic force. All right, I'll have to make that smaller. the strong nuclear force overcomes the electrostatic force and keeps the protons together in the nucleus. Again, the scales, I can't accurately do the scales on the board here, all right, but the strong nuclear force overpowers the electrostatic force and keeps the protons together in the nuclei of atoms. And now the example of the gravitational force working together with the spring force. Spring force is the force that a spring exerts on an object. Keep in mind that there are compression springs, and I will say that compression springs tend to push on objects, and expansion springs which tend to pull on objects. For example, if you take a compression spring that is this big and push it from both sides, so that now it's this big and you're holding it together. If you're holding the spring together here, tightly held together, and you put an object here and another object here, when you release that spring, it will push this object in this direction, and it will push this object in that direction. Right? So that compression spring, when you let it go, pushes outward on both objects. Now, what about the example of an expansion spring? What if you hang an expansion spring from a hanger of some sort, right? You fasten the expansion spring here, right? And right now it is not expanded, but then you put a weighted object, right? You hang a weighted object on that expansion spring. What's going to happen is the object's weight is going to pull that spring down, right? So now the spring is expanded, and here's the object, right, hanging from the expansion spring. Now, let's assume that the object is not too heavy, it doesn't break the spring, and the object stops right about here. Right? Now, this entire system is at rest, it is not moving, so you've got the weight of the object downward, that's Fg, that's a downward force, and you've got the spring force pulling up, positive Fs, balancing the weight of the object. We're neglecting the weight of the spring. We're making believe that the spring has no weight. Right? That's commonly done in physics when the weight of the spring is very small compared to the weight of the object. So again, this is an example of the spring force either working alone by itself or working with the gravitational force in a specific situation. The last force that I'm going to describe, again very briefly, is net force. And the definition of net force is the sum of all the forces on an object. But keep in mind that often we break this down into the net horizontal force and the net vertical force, or perhaps some other orientation that is more conducive to the problem at hand. In any case, let's look at a very simple example calculating net forces. And we will calculate a net horizontal force and a net vertical force, and they will not be the same. So, back to the surface, right? The top of a table, a floor. Here's the box. Now, let's say that the weight of the box, all right, Fg, is negative 20 newtons. The normal force that this surface is providing, F normal, is positive 20 newtons. This box is being pushed. Somebody is pushing the box, to the right with an applied force of positive 50 newtons, and the friction, which is opposing, we're trying to go that way, so the friction opposes the motion, right, or even trying to have motion. So the friction is going to be this direction, and the friction, this is going to be kinetic friction, the box is moving, all right, the kinetic friction is going to be negative 20 newtons. Now, we're going to calculate the net vertical force and then the net horizontal force. The net vertical force here, if you add up all the vertical forces on the box, the net vertical force is going to be 20 plus minus 20. 20 minus 20, the net vertical force here is 0. Now notice, net force is not a brand new force. We're working with other forces that we already learned. We're working with the gravitational force and the normal force. Now, what about the net horizontal force? All right, here are the horizontal forces. You've got the applied force, which is positive 50 newtons, and you've got the kinetic friction, which is negative 20 newtons. Add them together to get the net horizontal force. 50 plus minus 20. 50 minus 20 gives us a net horizontal force of 30 newtons. Now, just a really quick calculation of net vertical, net horizontal, so you can see a little bit of the equation, the math. All right? If we want F net vertical, and vertical is generally denoted with a Y, so you could put Fy, right? F net Y, F net vertical, whatever. You would take F normal plus Fg. So that would be F normal is positive 20 newtons plus negative 20 would be minus 20 newtons. So your net vertical force for this diagram is 0 newtons. All right? Now, what about our net horizontal force? Your horizontal, HOR, all right, generally speaking, horizontal is denoted with the letter X, just like on a graph. On the axes of a graph, horizontal is X, vertical is usually Y. You're going to add FA plus FF, in this case FFK. So we're adding FA plus FFK. FA is 50 newtons plus negative 20 would be minus 20, right? So your net horizontal force is going to be 30 newtons. Okay? So that's what net force means. You add up the forces. If they were both positive, you would add them. When one is positive and one is negative, you end up subtracting them. Right? Now, we've given simple definitions and very simple examples of all of the forces that we talked about. In the next 10 or 12 sections, whatever it is in the forces topic, we're going to go into much, much more detail about each of the forces and how they are used, and a lot more different examples from the real world, applications of the forces topic. I'll see you in the next section.